Okay, welcome to Chapter 7. Now, before we actually start Chapter 7, there's a few things we need to go over. Chapter 7 deals with right triangles. Now, the way that you solve for missing pieces of right triangles is by using the Pythagorean theorem. The Pythagorean theorem deals with squares and square roots. Now, in order to solve the Pythagorean theorem, you need to know how to solve for squares and square roots. This is where we have to kind of take a break, take a minute, take a day, or however long it takes. Remember, you can review these videos as many times as you need, but we have to stop, pause, and make sure that everybody's on the same page as far as how to solve for a square root, something that is also called a radical. Now, understand this. This is very, very involved as far as algebraically. Your math skills have to be great here, otherwise you will really struggle. Now, what we're going to do is we're going to work on taking these different square roots and breaking them down into their prime factors. That's what reducing radicals is. It's taking a number or a square root and breaking it down into its prime factors. And you'll see why here in a second. The first thing I want you to do is I want you to think of what is the smallest number that goes into 288. And we're going to start with 288. I know that it's even, which means that 2 goes into it. So what I'm going to do is I'm going to take, and right below the radical, I'm going to write 2 times something. What goes into 288 twice? Well, I know that it's 144. Now, you'll see that we didn't change the number 288. 288 just got broken down into a prime number. 2 is a prime number. It got broken down into 2 times 144. And the reason we want to do this, you'll see, is now I have the number 144 under the square root. Well, that's like saying the square root of 2 times the square root of 144. And now this is where your math skills have to be pretty good. You have to be able to say to yourself, what is the square root of 144? And I'm hoping you're saying to yourself, it's 12. Which means, and again, we still haven't changed any answers here. We're going to find out that the square root of 288 is a decimal, and our answer will be the exact same decimal. We didn't change our answer, we just changed what it looked like. And so instead of saying the square root of 144, I'm going to say 12. Now I'm still multiplying these two together, but instead of saying the square root of 2 times 12, I'm going to write it as 12 times the square root of 2. Now, to prove to you that we didn't change our answer, we just reduced it, I'm going to punch in my calculator what the square root of 288 is. And you can do the same thing just to double check my work. The square root of 288 is 16.97, and that's rounding to the hundredths position. Now I'm going to punch in 12 times the square root of 2 and see if that my problem has changed. Now, if I punch in 12 times the square root of 2, I get 16.97. Notice that my numbers are the exact same decimal, but one of them is reduced and one of them is not. The reason we want to reduce this is it's easier to multiply and divide this number, 12 square root of 2. It's easier to multiply and divide with that rather than 288. It's also important that you learn how to reduce radicals because, look at every other problem, every other fraction in math. We like 1/2 instead of 1632s or 250 over 500. We like numbers to be reduced. They're easier to work with. On your ACTs, you're going to see reduced radical form instead of the square root of 288. There are some times when you'll see a decimal, but a decimal answer is easy to find. We just use the calculator. The calculator, however, will not teach you how to reduce radicals. Let's keep practicing. Let's look at the square root of 112. Again, let's start with the number 2. Does 2 go into 112? Well, it does. We can take 2 times, and if you need to, you can just divide 112 by 2, and you should get the number 56. Now, 56 isn't a perfect square, and that's a term that you might want to write down and remember. Perfect square. And the reason you want to know that is, notice our previous problem. Once we found a perfect square, 144, we could stop the reducing process. That's where we actually solved it. So we're looking for perfect squares. Now I know 56 isn't a perfect square, so I'm going to continue reducing. I'm going to rewrite my problem, but instead of 56, I'm going to break it down again. 56 is even, so I know 2 goes into it, and I know that 28 times 2 is 56. Now at any point in time, feel free to stop this video or pause it and multiply the numbers that are under the radical. They'll always equal our starting number. 2 times 144 is 288. 2 times 2 times 28 is still 112. We haven't changed our number. We just changed what it looked like. Okay? Think of it in terms of finished cookies. Your finished cookies could be your raw products right out of your fridge. Your cookies could also be everything mixed together but uncooked, or your cookies could be everything cooked and on the cookie sheet or in my belly. Either way, they're still cookies. 112 didn't change here. We're just changing what it looks like. I'm going to break. How many of you are still laughing about the whole cookies in my belly comment? Grow up. Seriously. No, I'm just kidding. Don't grow up. Let's look at this number, and we can continue to break this down. Now, what I'm going to do is I'm going to keep breaking down 28 because I haven't gotten a perfect square yet. 2 times 2 times, and I'm still going to go with 2 because I know that 2 goes into 28, and I know it goes in 14 times. Well, I know that 14 can still be broken down, so what I'm going to do is I'm going to go 2 times 2 times 2, and then I'm going to break 14 down into 2 times 7. Again, just very quickly, you'll notice we just keep breaking down our larger number into prime numbers. Now this is what I want you to watch. 2 is prime, 2 is prime, 2 is prime, 2 is prime, and 7 is prime. We didn't hit a perfect square, so we couldn't stop and pull that perfect square out. But I do want you to notice this. I'm going to rearrange the numbers in this square root problem to form perfect squares. And you've got to know what a perfect square is. And again, this is algebra. A perfect square is a number that has 2 numbers, or 1 number, when multiplied by itself, that it equals. For example, 2 squared is 4. 4 is a perfect square. 3 squared is 9. 9 is a perfect square. And you can take that on up. But you'll notice that I can actually form a perfect square when I combine 2 times 2. I can get 4, and I can do that again. I want you to watch this. When I combine these 2 numbers, what I get is 4, 4, and then I still have the square root of 7 here. Now I want you to notice this. This is a perfect square. So is this. Just like the square root of 144. Because it's a perfect square, we can cross it off and write its true answer. What's the square root of 4? Well, I hope you're saying to yourself it's 2. Notice we're keeping our multiplication problems here. The square root of 4 is still 2, and we're still multiplying it by the square root of 7. Now what I want to do here is combine my like terms. 2 times 2 is 4. 4 times the square root of 7 is just the square root of 7. You'll notice that this problem took a lot longer, it took more steps, and it looks significantly different than the prior problem, the square root of 288 reduced. This problem, we had to figure out what its smallest pieces were and then recombine them to form a reduced radical. Now some of you might be saying, well, I knew that I could take 4 out immediately and get 4 times 28 and then break down 28 into 4 times 7. Let me kind of write this down so you can follow my thought process. Maybe the first thing you did to reduce 112 is say the square root of 4 times 28. And then you broke down 28 to say 4 times 7. And you'll notice that we got to the same point. The square root of 4 is 2. The square root of 4 is 2. The square root of 7 is square root of 7. So we still get 4 square root of 7 here. Excuse me if I'm going too fast. You'll notice that we got to the exact same point but took less steps. This is a way that you can use if your math and your algebra skills are where they should be or where they're supposed to be. This is a way to go slow, minimize your mistakes, break a number down into its smallest pieces, and then rearrange them. It's okay if you have a hard time understanding what we did here. It's okay. You should, however, begin to understand what we did here. Let me re-erase this so we can move on and keep practicing. What I would like you to do is think about 245. The last two problems we've used, we started by trying to reduce it with 2. That's not going to work here because 245 is not a prime number. It's an odd number. And so what I have to start doing is saying, okay, does 3 go into it? Does 5 go into it? Does, and so on and so forth up the prime numbers. Does 7? Does 13? Does 11? You have to be able to know how to reduce those numbers. If nothing else, just start dividing. Divide by 2, divide by 3, divide by 4, divide by 5, until you get a number that is reduced. I'm going to tell you right now that 3 does not go into it, but 5 does. And so I'm going to break down 245 into 5 times, and then on my calculator, I'm just going to divide very quickly 245 divided by 5. And what I get is 49. Now, I hope little bells and whistles are going off in your head, knowing that you can't break 49 down into anything but 7 times 7, or 7 squared. That is a perfect square. Meaning, when I rewrite this problem as the square root of 5 times the square root of 49, the square root of 49 has a perfect answer. It's 7. The square root of 5, is just a nasty decimal. We don't want decimals. We want reduced radicals. Well, the square root of 5 can't be reduced anymore, so I'm essentially done here, and my answer is 7 times the square root of 5. Now, if it means backing up and watching all these 3 examples a second time, go ahead and do that. But what you're going to need to be able to do this entire chapter is be able to reduce these radicals, be able to take a square root problem derived from the Pythagorean theorem, okay, in order to solve a right triangle, which, by the way, you're going to be using right triangles the next few chapters also. This is not something that just goes away. And next year in Algebra 2, or whenever you take Algebra 2, you have to use the square root and Pythagorean theorem also. You have to know how to reduce radicals. And so this is something that is going to help you down the line. If it takes rewinding this video and watching these 3 examples again, that's fine. You should begin to understand what we're doing though. What I would like you to do is pause the video, take a couple minutes, and try and solve the square root of 80. We're not looking for a decimal, we're looking for a reduced radical. Pause the video and try and solve that now. Okay, so hopefully you've taken time and solved the square root of 80 to reduce it. And you're going to see what I get. Now, I'll tell you what I got. I got 4 times the square root of 5. Let me write that down so you can see it. I got 4 times the square root of 5. Now, if that's not what you got, maybe you want to take a second, try and resolve it, and see if you can get the right answer. If you did get the right answer, or if you're just wondering how I got my answer, let me show you. The first thing I did was start off by breaking down the square root of 80, and you'll notice I didn't use 2. I started off and used 4. And the reason I know I used 4 is because 4 is a perfect square. If 4 goes into it, then 2 will work, and you'll see what I mean here. So I started off saying 4 times 20. Well, then I broke down 20 into 4 times 5, again identifying a perfect square. Well, because 4, 4, and 5 can't be broken down any further except perfect squares, what I then did is rewrote my problem square root of 4 times square root of 4 times square root of 5. It's like the distributive property. Because 4 times 4 times 5 is under the radical, I can rewrite it applying the radical or the square root to all 3. Well, the square root of 4 equals 2, so I can cross that off. The square root of 4 equals 2, so I can cross that off. And the square root of 5 is just the square root of 5. Now, I have a problem that reads 2 times the square root of 5. I can combine 2 times 2 here and actually get 4. The square root of 5 nothing happens to that. It doesn't change. It doesn't become the square root of 10. It just stays the square root of 5. And so that's where I got my 4 times the square root of 5. Hopefully, again, you understand how we did these 4 problems. And if you need to, pause the video, rewind, watch them again, because tonight's homework is very, very intensive. It's a lot of this. Now, there's one thing I'm going to say before we actually look at your homework tonight. There are times when your number cannot be reduced. There are times when you get a perfect square into the radical that cannot be reduced. And I'll give you an example. The square root of 57. one number off 56 and one number off 58. 56 can be reduced, 58 can be reduced. But the square root of 57 is a perfect prime number. Nothing goes into it except 1 and 57. It cannot be reduced. There are going to be times tonight when you get problems that can't be reduced, and that's perfectly fine. At that point, when it can't be reduced, when you can't pull any perfect squares out, leave that as your answer. That is reduced. And although it's a big number, it's bigger than 12 square root of 2, 7 square root of 5, 4 square root of 5. Even though that's a bigger number, we can still use it. You need reduced answers though. Let's go ahead and look at the next page because this is where your homework is derived from. If you look at this guided practice problem, or set of problems, excuse me, you're not only going to see that you have to reduce radicals, you're also going to see that you can apply division properties and multiplication properties to radicals. And what I mean by that is this. You can tell that 4 times the square root of 4, these are like terms. 4 or square root and square root, that's like a like term. Now forget the fact that the square root of 4 is 2 and 2 times 2 is 4. What I want you to see is this. The square root of 4 and the square root of 4 multiplied gives you the square root of 16. The square root of 16 can be reduced to 4. You can also take and look at number 6. Let's do number 6 together. You can take the square root of 25 times the square root of 28, and you can get, if I turn on my calculator, you can get the square root of 700. Now, I know right away that the square root of 700 can be broken down into 100 times 7. You might ask yourself, why did he use 100? Let me show you. 100 is a perfect square. The square root of 100 times the square root of 7 can be reduced to 10 times the square root of 7. Because the square root of 10, or the square root of 100 is 10. And so for number 6, my reduced answer can be 10 square root of 7. Now you can try and reduce these, okay? You can reduce them first and then multiply your like terms, or you can multiply first and then reduce. That's up to you. You can also divide. And let me show you what I mean. Let's say we take our same problem, or our same answer, 10 square root of 7. And let's say I was told to multiply that by 1 over 10. Well, when we multiply with any fraction, we multiply straight across. 10 square root of 7 times 1 is 10 square root of 7. Well, when I carry the 10 over, notice this. 10 is on top, 10 is on bottom. They cancel. I'm left with the square root of 7. That's reducing. That's reducing a radical. It's just like reducing a fraction. Okay? Let's look at problems 9 through 16. You can also apply the distributive property here. And I'll give you an example. We have here the square root of 25 divided by 100. Well, I can rewrite that as the square root of 25 over the square root of 100. Well, 25 and 100 are both perfect squares. The square root of 25 is 5. The square root of 100 is 10. Notice this, I'm left with a fraction. Now, you can choose to reduce that fraction or not. Eventually, you will have to. But for now, 5 over 10 is good enough. It's reducing the radicals. It says use the quotient property. You also, if you look at number 11, you might have to reduce a radical and then multiply. So this is getting a lot more intensive than just reducing a radical. But make a mental note, because if you struggle doing this, then you're really going to struggle when you get to these. And yes, we have to do this. I'll give you an example. When you deal with a special right triangle that is 60, 30, meaning there's an angle that's 60 and an angle that's 30, and the other angle's a right angle. One of the properties of a 60-30 is that one side is one length, and then you can multiply that leg by the square root of 3 to get the other side. So you have to learn how to multiply. And there are further examples that you're going to see when we get through Chapter 7. But for now, what you need to do is go through these problems. And I'll make it easier. I know you're saying to yourself, these are a lot of problems. What I'd like you to do is pick 2 problems from the top section. Let me erase this so you can actually see what I'm talking about. Pick 2 problems from this group. Pick 4 problems from this group. And all you have to do is pick 6 problems from this group. Now, some of you are just going to pick the top 6, because those are easiest. That's fine. If you want to do that, that's fine. You're still going to have to learn how to reduce radicals. But I'm telling you, don't be afraid to take a couple challenging problems. Okay? You look at number 28, you look at number 16, you look at number 8, and those are obviously harder than, say, 5, 17, and 9. But at the same time, and by the way, you can't do problems that I already did. So 9 is out of the question. I already did 6, so it's out of the question. Don't be afraid to challenge yourself. I mean, you're not getting graded on this assignment. It's participation-based. Challenge yourself. Try and see if you can get some of these correct. Or even if you get them wrong, let's identify, when we go over this assignment, let's identify what you did wrong so we can fix it. Go ahead and work on that tonight, and we'll see how you did tomorrow.